All right. Um, so, what I'd like to do is start talking about something in 4.1 that comes in towards the end. I think most of the rest of the very first part of chapter 4 and 4.1, I think a lot of it's pretty self-explanatory, and a lot of things make sense. Sort of some basic definitions of sets. Um, One thing that he brings up at the very beginning is category theory. I'm not really going to talk that much about category theory. I suppose you could let me know if you have any questions about that. Um, but that's a separate branch of mathematics. But sets are really important, and a lot of things involve sets in a way. There's also some relationship to logic that's brought in that is kind of interesting to see that relationship between that. I'll also talk a little bit about, maybe towards the end of chapter 4, when we're talking about Russell's paradox. I may talk a little bit about what's referred to as a Boolean algebra and tell you kind of how that works, because it's pretty neat. What I want to do is talk about power sets a little bit, the idea of what a power set is, and then kind of how we're gonna work with them. So we have a set, right? I'm going to call a set A, right? It has elements A, B, and C in it. Made the wrong kind of bracket. Right, so A, B, and C. I can make the power set of that set, right? I call the power set of A. That is a terrible curly bracket. Oh well. It's really the set of all subsets of set A. So any possible subset I could make. Now, whenever I have a power set of something, one thing that's always included is the empty set, right? Because, the empty set is a subset of every set. That's kind of interesting. So a subset could have no elements, right? Then we can have all of the singleton sets, right? All of the one-element sets that exist. So there's A, B, C. Then all of the two-element sets. So I've got AB. Then I've got this set AC. And then this set BC. And remember that when I have a set, the set AB and BA are the same set because they contain the same elements, right? So those are equivalent sets. Those sets are what we would call equal, and we can talk more about set equality at some time later. But so there's all the two-element sets, and then finally the three-element sets, right? So I've got set A, B, C. So it's perfectly valid to have a set be a subset of itself. That's true of all sets. All sets are subsets of themselves by our definition of what a subset is. We'll talk more about that in the inclusion section, which is coming up next. But there we go, right? This is all of them. Now, something the book hints at in a few places, but doesn't make it explicit, which I think I would like to, is that, if I want to count the number of, let's say, 0-element subsets, or 1-element subsets, or 2-element subsets of some given set, right? How do I do that? Well, it turns out that we use, our old friend, the binomial coefficient, right? So if you remember this thing, right, in choose k, right, sometimes it's referred to. You see it this way. Another way you might see it is written this way. You'd have an in, and then a big C, and then a K. These are, sometimes you would see this in like a book, a probability book or something like that, and you might see it written that way. But I think it's not uncommon to see it as the brackets. Especially, we've seen it a few times in the class when we were looking at binomial theorem stuff, or it comes up all the time. It seems kind of weird maybe at first, but if you think about it, it's really not that weird that we would be doing this choose function in choose k, because like let's take our example, right? We have a 3-element set, right? So n is 3, and for the number of 0-element subsets, right? Notice I'm choosing 0, right, out of that set of 3. Right? And if you remember, it's n factorial, I'll write it over here, right? This is n factorial divided by, that's k factorial times n minus k factorial, right? And so here, right, I've got 3 factorial divided by 0 factorial times 3 minus 0, which is just 3 factorial. 0 factorial is 1. I mean, 3 factorial is 6 if you really want to calculate it, but it's really unnecessary because you've got 3 factorial divided by 3 factorial, whatever it is, it's just going to be equal to 1, right? And notice that gives us, right, as is done before up here, right, here is our number, right, there's our 0-element subsets, there's only one of them. So that's kind of interesting, right? And if I want to count the number of 1-element subsets, this would be, right, it's going to give us 3, right? We've got 3 factorial over 1 factorial times 2 factorial, which is 3. Right. 3 choose 2, that was a bad one. Also gives us 3, and then 3 choose 3. That gives us 1, right? So notice if I want to count up the number of, well, let's say the number of elements in the power set, right? So if I want the cardinality of the power set, I could just add up all of these numbers here, right? So notice that in this case, we have this power set of A, and that's going to be 8. Yeah. Now, something I'll say is that if we have a set, right? So if I have a set defined, like let so let B be some set with elements B1, B2, right? Let's say all the way up to BK, right? Notice that this means that the cardinality of B, right, is K. Now, if I wanted to find the size of the cardinality of my power set, right, for B, this is an interesting theorem that comes up. It's 2 to the power k. And perhaps we'll probably prove this at some point when we learn how to do induction proofs, because induction makes this proof actually, it's not a trivial proof, but it's much easier than doing it another way. Another interesting thing I think that this also implies, actually, it gives us a very interesting implication, which is that the sum of, let me use a k instead. The sum of k equals 0 to n of n choose k is 2 to the n. This is another proof we can do using induction, and so maybe that would be something interesting to look at in the future. All right, I'll show you the next video soon.